Welcome back to The Explainer. Today we're doing something a little extreme. We're taking a journey to the most bizarre, the most powerful, the most mind-bending objects in the entire universe, all to answer one simple question. What actually happens if you fall into a black hole?
So, to help us on what is definitely a one-way trip, we've got a volunteer. Meet the little robot, or LR for short. Its whole mission? To dive headfirst into that abyss and send back as much data as it can. So we don't have to.
So the big question is, what's going to happen to our little guy? I mean, what does that even look like? Is it going to get crushed, stretched into a noodle, or is something even weirder waiting for it? Right there at the very edge of everything we think we know about physics.
All right, here's the plan for our trip. We're going to start with the aptly named spaghettification. Then we'll get into why size really matters with black holes. We'll look at the edge of infinity itself and then see a showdown between a brand new theory of gravity and the classical view. And finally, we'll ask, what could possibly lie beyond the singularity?
Okay, first stop on our tour, spaghettification. And yeah, it is one of the best named concepts in all of science. And trust me, it's pretty much exactly what you're imagining.
So, what is it really? Well, the whole idea is that a black hole's gravity is just unbelievably intense. It's so strong that it doesn't pull on an object evenly. The part of the object that's just a little bit closer gets pulled way harder than the part that's farther away.
So picture our little robot, LR, falling in feet first. The gravity yanking on its feet is just exponentially stronger than the gravity pulling on its head. And that difference creates this incredible, irresistible stretching force that just wants to pull it apart, top to bottom.
But get this, it's not just about stretching. At the exact same time it's being pulled into this long, thin wire, there are other massive forces squeezing it from the sides. So you're being stretched and compressed all at once. It's how you make spaghetti, right?
All right, but here's where it gets really weird. Kind of counterintuitive, actually. Whether our robot even makes it across the event horizon, that point of no return, all comes down to one thing: the size of the black hole.
Okay, so check out these two graphs. They tell a really wild story. Both are showing the tidal force, that's the stretching force, as you get closer to the event horizon. Now, for the supermassive black hole on the left, look at the force right at the horizon. It's not that bad. You could actually cross it. But now look at the smaller, stellar mass black hole on the right. The curve has the same shape, but the force at the horizon is, well, it's catastrophically huge. Worlds apart.
Just how huge are we talking? Well, for a stellar mass black hole, that stretching force on our little 1 kilogram robot, right at the edge of the event horizon, it would be 10 billion newtons. That number is just staggering.
Okay, to put that into perspective, that's like instantly hanging a 1,000,000-ton weight from the robot's feet. 1,000,000 tons. It wouldn't just get spaghettified. It would be ripped apart into its constituent atoms long before it even got close to the horizon. Game over.
So let's say our robot chose wisely and went for a supermassive black hole. It crosses the event horizon in one piece. Now what? To answer that, we got to look at the classic picture, the one that comes from Einstein's general relativity. What does it say happens at that point of no return?
Right, so here's the standard model, the textbook version of a black hole. You've got the event horizon, that's the outer boundary, the point of no return, and then, right in the heart of it all, is the singularity. That's a point where all the mass is supposedly crushed down into zero volume, which means infinite density. And that's where things get weird.
Now, according to Einstein, if we were watching our little robot fall in from a safe distance, we'd see something totally bizarre happen to time itself. We'd see its own clock start to tick slower and slower and slower, and as it gets right up to the edge of the horizon, it would look like it just freezes. It would just hang there, getting redder and dimmer, stuck in that one moment for all of eternity, from our point of view.
But hang on, whenever physics comes up with an infinity, infinite density, time stopping infinitely, that's usually a big red flag that the theory is missing something. It's a sign that our understanding might be incomplete. And that's where a newer theory comes in, one called Dynamic Newtonian Advanced Gravity. And it suggests a completely radical rethink.
So this theory, they call it DNA for short, basically rewrites some of the equations for gravity. Now, in most everyday situations, its predictions are pretty much the same as the classical view. But when you get to the insane extremes of a black hole, it changes the picture completely. And critically, it gets rid of that pesky problem of infinity.
And here is the absolute key difference. Instead of time grinding to a complete halt, DAG predicts that right at the event horizon, time for our little robot just slows down. And it slows down by a very specific, very finite amount, a factor of 1.5. That's it. No infinity, just a number.
Okay, so we've got a showdown. Two completely different predictions for what happens right at the edge. So how do we figure out who's right? Well, we look at the evidence. How do these two ideas stack up against what we can actually see out there in the cosmos?
So this really lays out the two different paths. You have classical gravity on one side. As you get closer and closer to that event horizon, time dilation just skyrockets up to infinity. The physics literally breaks down. Then you have DNAg on the other side. The line curves up, sure, but it smoothly peaks at a specific finite value. Here the physics gets weird. It bends, but it never ever breaks.
You know, this table is actually pretty cool. It's showing the predicted time dilation at different distances. Now look way out. I'd like 10 times the radius of the event horizon, or even 5. The two theories are basically giving the same answer. They're identical. But then, as you get closer, boy, do they start to disagree. And then right at the horizon, one theory just breaks. It goes to infinity. The other one, it just lands nicely at 1.5. It's a huge difference.
And look, this isn't just some abstract mathematical idea. The DNAg model works. It perfectly predicts the time dilation effects we see in our own GPS satellites. You know, the ones we have to correct for every single day to make them work. What's more, when we look at the light coming from near the real black hole, Cygnus X1, the predictions from DNAg seem to be a better fit for what we actually observe than the old model.
So, what does this all mean? If this DNA theory is pointing in the right direction, what does that mean for our poor little robot? And maybe more importantly, what does it mean for how we understand the entire universe?
Well, for our little robot, I'm sorry to say, the end of the story is still the same. Spaghettification is going to happen. But for physics? Oh, the implications are absolutely massive. If DNAg is right, it means singularities, those impossible points of infinite density, they just don't exist. It means the universe has a way of avoiding the absurdity of infinity, which is something physicists have been dreaming about for decades.
And that's really the point, isn't it? Black holes aren't just cosmic vacuum cleaners. They're nature's ultimate laboratories. They take our best theories, our most fundamental ideas about reality, and they stretch them until they break. By forcing us to deal with these impossible infinities, they show us exactly where our understanding is incomplete. They're pointing the way to a newer, deeper physics. The real question is, what else will they reveal about the universe when we finally learn how to listen?